All right. Hi, everyone. Welcome to Breaking Down AI for Recycling, or as we like to call it, AI for Recycling 101. Before we get started, just wanted to go over a few housekeeping items. First, we will be recording this webinar and we will be sharing the recording over email, which will be sent out sometime next week. We will also be having a live Q&A at the end, so please put any questions you have in the Q&A box at the bottom of your screen. With that, I'd like to introduce our speakers for today. We have Apurva Pradhan. He is the head of product here at Everest Labs, and Katie Nellis, who is our solutions engineer at Everest Labs. Before I pass it off to our speakers, I just want to run through the agenda real quick. This whole webinar is about breaking down what AI for recycling really means. So we're going to start with an overview of AI for the recycling domain. We're going to then talk about use cases for AI in the recycling chain as a whole and in MRF specifically. And then we will talk about integrating AI into MRF operations and how a typical Everest Labs deployment works. And at the end, we will wrap up with a real world example. So with that, I want to thank you all for being here, and I will pass it off to Apurva.
It's good to be here to talk about AI for recycling. I'm also very excited to share the stage with Katie, who has a ton of experience advising MRFs and reclaimers and recycling companies in general about how to implement AI. So she'll have a lot of great examples, hands-on examples for you. But I'm going to set it up for her by just going through the basics, the whys, the what, and then Katie will really go into the how. But I'll start here. The first comment I'll make here is that recyclers face an uphill battle when it comes to operational efficiencies in their plants. And when I say recyclers, I'm mostly talking about material recovery facilities, but same is true of reclaimers and reprocessors. Most material recovery facilities, in my experience, have four really high-level goals that they're trying to achieve, right? They're trying not to be a bottleneck in the recycling process. So what that means is they're trying to take recyclables from the source, which is homes and businesses, to either landfill or to the end market where the recycled product will be used again. And if homes and commercial businesses continue to generate recyclables, a MRF cannot really be the bottleneck there because it has to go somewhere. They're also in the business of producing high quality recycled content. The higher the quality, the better price they can get for that. And this is especially important in today's world where there's a shortage of high quality recycled content. They're also, trying to operate profitably just like any other business would. And they're also trying to meet regulatory requirements that are placed on them either through municipal contracts or through evolving recycling policy. But there's some challenges that they have to overcome to be able to achieve those goals. Namely, the challenges, the three of the biggest challenges that we see are listed here. They're dealing with a really chaotic stream of material that they often don't have a lot of visibility into to be able to react and operate efficiently in collecting and sorting that material. They're also dealing with aging equipment that were set up at the beginning of when the plant was made and really have not gone through optimization and changes since then, and which leads to sort of lower sorting efficiencies and higher costs. And they're really dealing with an environment where they have to pay a lot of money for labor, for processing costs, especially compared to what the end market that they're selling into is buying the materials that they're producing at. So the picture you see here on the right-hand side is on the red line up kind of a baseline of processing costs. And then the dotted line is sort of the material costs that they can command. And in a lot of the times, a lot of the periods that you see here, the material costs that they're able to get are under the processing costs. So a very challenging business to operate. And so all of that in the way of saying that in order to meet these goals, you need to be able to improve the operational efficiency, and you really can't improve what you can't measure. Um, and that goes into sort of the the AI part of this. So what does it take to measure the recycling stream, which is something that we want to give you a little bit of deeper insight into. Before I get into sort of the details, I want to run a quick demo by you. What you're seeing here on the left-hand side here is a typical conveyor belt carrying recyclables. What you're seeing on top of that belt is a vision system, one of our vision systems, which is observing the material flowing under it. And that data then makes its way into an AI model. I'll go into sort of the basics of the model, but the model really what it's trying to do is identify these materials. Now, here's a little demo for you. So what you're seeing here is, I'm going to play this video, and this video will basically play out the contents that it's seeing on this belt. If I pause here, when the belt is not very heavily um, burdened, you can kind of, a person would be able to identify these materials and be able to count them and give you a decent idea of what's on the belt. But the instances where materials you can see and identify manually is not a common thing. What you'll see is these belts get denser and denser over time. So here you might be able to still count the number of objects and tell you what it's made of, the composition is made of. But once you get into scenarios like this, there's no way that a person would be able to identify any of these materials. There's just too much and too fast. And so we need to automate this to really know what's in the recycling stream. And that's what the AI does. So recycling, is one of the identifying materials in the recycling stream is probably one of the hardest environments, data environments for AI models, for these reasons listed out here on the left. It's a extremely unstructured data environment. So there's a lot of variation in how objects appear. A container or a can may look very different when it was first created to when it ends up in a recycling facility. The amount of variation in that material is extremely huge. Like take, for example, if you compare this with another AI application, for example, like a self-driving car, a car generally looks like a car. A bicycle generally looks like a bicycle. A person crossing the road generally looks like a person crossing the road. Whereas if you take a aluminum can and you look at it in different recycling facilities or different locations within the recycling facility, they look very different from each other, often unrecognizable, right? So it's an extremely unstructured data environment. It's also the data is heavily what we call imbalanced. So your AI model has to be bias resistant. What that means is in some facilities, or in some lines, or in certain locations within a facility, you'll notice a lot of a certain object for very little of another object. And you go to another place, it might be completely different, right? So the same model has to be able to identify objects in this sort of data imbalance environment with heavy data imbalance. We have to make inferences very, very quickly. As you saw, there's hundreds of objects in the belt, and these belts are moving anywhere from 100 to 200 feet per minute. So you don't have that much time to make an observation. Again, if you look at something like, if you compare this to something like self-driving cars, cars actually have quite a lot of time when you're looking, the cameras in the cars have quite a lot of time when you're looking at the objects to be able to determine what that object is, that something's in your field of view for a long period of time. Here, in the recycling case, the objects in the field of view for, maybe a fraction of a second. And you have to be able to make inferences that quickly. You also have to rapidly fine tune the output of the model. What that means is every facility is different, every line is different, lighting conditions in lines are different, material conditions are different, the belt underneath it is very different. So a model needs to be able to recognize those differences and take out those differences in making those predictions accurately as you move from one location to another. You need a very versatile ontology. What that means is, material packaging classes and materials that we're trying to identify change over time. There are new objects being added every day, so the model has to be able to have headroom for these types of new packages or new appearance of an existing package. You also often want multimodal data support, which means that you're not just relying on images to make these inferences, but you can also utilize text within those images or even spectral scans of those objects that you're looking at. And it has to be edge optimized, right? So because we're trying to make real-time decisions based on this data, the model has to run not in a large data center with infinite compute resources, but within a relatively low-cost computer that's running a GPU that's in the plant next to the vision system. So it has to be optimized for those types of machines. And so there's a lot of things that we have to take into consideration when you're designing an AI for the recycling stream. This gets into the overview of the AI model that we use at Everest Labs. Also, probably a similar architecture for a lot of the models that are used for identifying recyclables. But what we're dealing with is really a deep learning network with supervised learning, which means that the model is learning on images that have been labeled by humans, and therefore, it can make relatively quick assessment of that object. The size of the AI network really depends on sort of the cost, the performance, and the speed at which you're trying to make these inferences. As I mentioned, we're trying to make these inferences within milliseconds on the edge. So that really limits the size of the AI network that you can use. And really, a lot of it depends on the data set that you've used to train these types of models. The data set that we use at Everest Labs consists of well over 1 billion instances of different objects balanced across 60 different classes of material that we can identify with over 95% accuracy. This model has been learning and training and retraining itself for the past 6 years. So it's a fairly robust data set. And as I mentioned, we look at sort of the object appearance, the text and images within the object, and even be able to augment kind of vision-based data with spectral data, whether it's a line scan or a spectral image. All of these can be put into the data set, which really means this is a multimodal data. Now, it's great to have an AI network that can make these inferences, but you also need a lot of ongoing processes to make sure that you're not drifting away from your accuracy goals, and you're not drifting away from sort of the baseline of the model. So we've got model testing framework and ongoing model training that's contributing to the data set and then therefore contributing to the performance of the model. And there are also Gen AI features that we've added in, which allows you to synthesize data based on a few instances of objects, be able to synthesize data so that they can feed the data set for objects that are not very frequently available in the locations that we go into, or have kind of very different appearances in different locations that we can go into. We can use generative AI to generate the data sets needed to retrain these models. And the models really pull out specific attributes about an object, right? So it'll tell you what material it is. It can tell you what kind of packaging it is. It can tell you even things like who made that packaging. It can give you idea of its size and height and therefore estimate mass. It can tell you things like motion, you can do motion planning to be able to accurately land sorting devices like robotics onto that object. It'll identify optimal pick points for you. It can even go as far as calculating for you what the value in terms of energy savings and in terms of greenhouse gas savings if you happen to pick that material. So you can use that data, you can use that information to sort of prioritize what you do. So that's sort of the basics of the model. But outside of the model, as I mentioned, you really need a robust AI infrastructure to be able to have these models be useful in production. This is an image of an architecture we use to make sure that the models are performing as it should. So we've got a fleet of vision systems installed in recycling plants. All of that data is going into a secure server, and from there, there's sort of two tracks that the data takes. One is using that data to generate KPIs around whether that plant is operating efficiently or not. So tracking performance, optimizing equipment within the plant remotely, providing alerts and notifications to the staff on the ground if actions are needed. But the other track that the data takes is to be able to make sure that the model is performing up to the SLAs that we provide to our customers. So we're auditing the model is being continuously audited. It's being trained, continuously trained. And also as new models get generated out of the new training data, those models are able to instantly be able to be installed in all of the machines that are running, so that you have kind of consistency across your fleet of vision systems. Um, once you get good at identifying recyclables in the recycling stream, there are a lot of use cases for that AI model, right? And so this is a picture that I lifted from the internet, but it gives a good picture, good flow of the recycling value chain, starting from sort of hauling trucks to going to processing facilities like material recovery facilities, to going to reclaimers, which then turn that material back into virgin material, going to package, the packaging company creating packaging out of that, which go into businesses, and ultimately end up back in recycling facilities. There's a lot of use cases for AI in this whole value chain. So the AI can be used to identify, contaminants, identify what they call overages in using videos that are coming out of recycling trucks. What we specialize in at Everest Labs is really helping material recovery facilities process household and business waste and recyclables, so that AI can be used for plant monitoring and automation, robotic sorting, automating other sorting equipment in the plant, as well as kind of sort of continuous monitoring of plants. This is the part that Katie will get into more in the next few slides. We can also use that AI to make the reclaiming process better, basically being able to more efficiently process the recyclables back into raw material. We can also provide packaging companies with insights that they need to do a better job of designing more sustainable packaging. The AI can also be used to help deal with recyclables directly on site for large producers of waste and recyclables, like campuses and stadiums. And then the data can ultimately also help brands with their sustainability efforts and circularity efforts. So there's a lot of use cases for AI once you can identify these recyclables accurately. And as I mentioned, I'm going to turn it over to Katie to really talk about how we help the material recovery facilities and give you some hands-on examples.
Okay, thanks, Apurva. So here are the use cases for Recycle data in that MRFs part of that recycling chain. And those use cases can be designated kind of into these three overall segments here. We've got material characterization. So our vision systems are essentially digital eyes that can identify the composition of all your recyclables and your residue streams wherever we place the cameras. For equipment optimization, placing our systems on your QC lines throughout your plant can uncover insights into how effective your other systems are operating, like your screens, your eddy currents, and your other types of separators. This data provides a feedback loop that allows you to configure those machinery for optimal performance. And overall, strategically placing these multiple vision systems throughout a plant will garner analytics showing you how well your entire operation is performing. And you also get to see what impacts can happen as a result of changes in your material flow or changes that you make in your processes. So the more data you have, the more you can do with it, and the more control you have over what's happening out on the floor. Okay, where in a MRF can we specifically put our vision systems to provide useful data? I've had the privilege to tour over like 30 different recycling plants in North America, and while no two MRFs are the same, this map here covers the common equipment and standard material flow that residential and commercial MRFs can hopefully relate to. So each bubble on this map is where we could replace our Recycle OS AI. Numbers 1 and 2 cover your pre and post screens or any separator that is after pre-sort, but it's really your first fiber and OCC separation. This allows you to assess your incoming material stream, what composition is recyclables versus residue. Knowing how these systems are performing at the front of your MRF allows you to tune belt speeds, you can redirect material and help optimize for your downstream processes. You can use the data to compare incoming material to the contracts that you have with your suppliers and also monitor any, pre-sorting issues or errors you might have. Numbers 3 and 4. Let's say your MRF is using optical sorters. Putting AI before either a fiber or a container or 3D optical can allow you to monitor how your 2D versus 3D separation is doing. You get your fiber and your OCC and your container compositions. You can understand kind of your primary recyclables capture rate. And it provides feedback to fine tune the parameters of your opticals, what it's firing on and what it might need help with. And any influx of OCC or fiber or containers that are ending up in the wrong stream, using our cameras here, you can identify that and track over time, if your screens or separators need maintenance or they're having a failure, things like that. Bubbles 5, 6, 7, and 8 here. These are your QC lines. These could be after additional opticals or after an eddy current or a magnet. The AI and data on these QC lines identifies your major commodity recovery rates. You can track your bale or your bunker composition and purity. And again, monitor any upstream equipment errors. So like if a drum magnet breaks and it's just spinning, but it's not pulling anything off, or if the eddy current angle needs to be adjusted, things like that. Bubble 11, this is your last chance. Your last chance or your residue line. And this is a popular and effective place to start with Recycle OS AI because you get your residue composition without having to do manual audits. So you can see the tonnage and the dollar value of what recyclables your system is missing, essentially what could be net new revenue if you captured it out of your stream. So you can also understand what your landfill or hauling losses are by the fact that you're sending those out the door to a landfill. So a lot of our clients use this data strategically to determine if adjustments need to be made to how they're processing. They can use it to perform maintenance or add automation equipment like robotics in order to increase their recovery rates. And lastly, bubble 12 on your baler line. Here you get data on your bale composition to sort of verify your purities. You can audit what materials you're actually sending off to your clients. And on certain lines, we can perform some mass balancing estimates. It's all useful data for whatever system you use to track and trace your bales. Okay, here are some photos of our vision systems out in the wild in production at US sites. Last chance on the left here. As I mentioned, having AI on your residue or your last chance line can be really eye-opening. In this photo, you can see it mounts directly on top of the conveyor, either with bolts or with welding. The camera itself is housed inside that black box to keep dirt and dust off of it. It's about 2 feet thick, of 2.5 feet tall, and the width of it can actually be adjusted to the width of the belt. It's also self-lighted, and there is a compute box that is installed along with this, either in the area of the conveyor where the camera is, or it can also be installed in a central server room if your facility has one. But no major retrofits are required in order to install these. In the middle, we have a fiber QC line. I chose this photo because it's actually on an inclined belt. So the camera can be installed on flat or an inclined belt. It doesn't matter. We just need the sloped belt to have cleats so that the material doesn't roll back, which is like what you can see in this photo. And because this is a fiber QC line that it's on, it's also pretty wide. So you can see how we can configure that box in that system for that size belt in that photo. Lastly, on the right, we have a portable mount for our vision system. It's an even smaller footprint than our standard camera box, which allows for us to place our AI in tight spaces. And this can also be leveraged for temporary data capture if you wanted to gather insights on a line for a short amount of time. So yeah, these are just a glimpse into what our systems look like out there in the wild. So now I'm going to actually toggle over to give you a peek into what data from these cameras looks like. So this is me logging into our RecycleOS analytics platform, which is a browser-based system here. And this is a dashboard or a data set that we have from a project where we put about 6 vision systems throughout a MRF in the Pacific Northwest. And this particular MRF wanted to know where their material was ending up, right? So our systems allowed them to determine if material was ending up in the proper QC line or in their residue or everywhere in between. So you can see in this mass balancing where the material, started and then where it actually ended up in the system. And you can see even from this one data set, this is a MRF that is collecting both color and natural HDPE, but they're baling it together in one HDPE bale. And so they wanted to know if they were to try to bale those two separately, not in a mixed, where have those materials been going in their system and where would they need to properly recover it? So this use of our vision systems and our AI helped answer that question for them. So how do we turn this idea of AI into a reality at your sites? This is a high-level deployment process that we follow to implement our AI into your MRFs. In scoping, we start with a site survey, which is a free service we offer where someone, likely me, will come out to your site and spend a couple hours with you to really learn about your unique operations, what you excel at, what your struggles are, how your material flows. It's a very hands-on sort of discovery session where we'll walk through your MRF from tip floor to residue, understand the flow of everything, the equipment that you have, even the equipment that you're hoping to put in. I'll take a bunch of measurements and different data points and then use all of that information to go back and to design a solution that's like tiered to your needs. Just like my slide before with all the bubbles on it, we'll map out the areas of opportunity in your specific MRF flow where AI and data can be useful. When it comes to planning, if you opt to install one or multiple of these systems, we'll begin by sort of formalizing the requirements of what data and analytics you're looking for. And our awesome deployment team will draft out an installation plan and schedule the dates for that. All the while, your teams on site will help by preparing any power or Ethernet drops that are needed. Then comes the actual install. The hardware gets shipped out and our deployment engineer will come on site to lead the installation, which we say takes about 1 day to install, but the physical installation onto the belt really only takes like 1 to 2 hours of time. But our engineers can work on your breaks, on your scheduled maintenance hours, on off shifts. They are the troopers that will work around the clock for this to avoid downtime in your normal processing hours. The rest of the time in that day of installation is really spent installing that compute box that goes with it and making sure that everything is connected and up and running. But once it's on, we're gathering data. And over the next 1 to 2 weeks, we will remotely fine-tune the model to your specific conveyor and the use case there, getting to that 95+% accuracy of identification on the line. As that fine-tuning is happening, our data team is configuring your RecycleOS analytics dashboards, which we can then take you through and have sort of a model alignment period where we're reviewing the data. You're giving us feedback on what data sets are useful, what may need some tweaking. You're really just starting to learn and be trained on the insights there. So ultimately, you can use that to make decisions and take action. Okay, this is a list of all the sorts of services that you get when you choose to lease or purchase one of our vision systems. It's not just a camera that we slap on a belt and then walk out the door. Like I said, once it's installed and it's running, it's also improving. We have that professional monitoring team at our robotic ops center that's auditing the model performance. We come with performance and uptime guarantees. Like I mentioned, the analytics that you get with this are vast and vary based on what belts these cameras are put on. And any improvements that we make to our base model, whether that be a security feature or identifying a new packaging class, those updates can get introduced to your systems as soon as a model update can be made. And of course, you get full access to that RecycleOS data platform, which I really just scratched the surface of today. And there's also hardware and warranty and technical and maintenance training, but a lot of that is actually much more applicable to our robotics. Our cameras really do not require regular maintenance, besides maybe a dust off every month or so. And yeah, this AI in MRFs it's not just a concept. Our cameras and our AI are out there in production, providing value to MRFs all across America. So this case study highlights a MRF in the Pacific Northwest that they're processing around 200 tons per day. They knew they were losing a lot of recyclables to landfill, but they weren't sure exactly how much. So they chose to install our AI onto their residue lines or their residue line, excuse me. And the insights were major, totaling across UVC, PET, and HDPE. They found that over $650,000 of those materials were getting missorted and sent to landfill every year. And that lost revenue was the data that they needed to go and upgrade their upstream processes. They made changes to their eddy current and optical sorter, and they even changed how they were manually staffing their plant. All those changes allowed them to recover about 70% of that lost value, which was over like $450,000 in those commodities annually. So this is very substantial success for that MRF. And like we've kind of hinted at, until you have eyes on this types of things that can be happening in your MRF, you really don't know what you're losing or what you could be doing better. Okay, so this webinar laid out how AI works, how it can be applied in recycling, how it's currently being utilized in the MRFs, and I've been talking about it for a while, but I want to end on this sort of forward-looking perspective of AI and in recycling. Like, what is next? EPR programs are going through legislation and being enacted across the country. Recyclers will and should anticipate pretty rapid changes in what is required of them to recycle. And also those recyclers will need to be able to provide data on that, right? So our AI can be trained quickly on new recyclable packaging that will come out of our producers and these policy changes. And those new laws can drive an increase in demand for recycled content. So being able to inform your downstream clients on your bale qualities will benefit sort of the entire circularity chain. Branding is also a very cool innovation that AI can deliver, being able to recognize, to categorize, and count the branded packaging on a line will allow companies to track their recycling goals and provide feedback on how sustainable packaging is doing. And putting it kind of simply, the very nature of AI and how it's built is to be continuously learning and is to be adaptable so that it can keep up with the changes that are happening quickly in this industry. And it's only going to continue to innovate how recycling gets done.
All right, sorry about that. All right, thanks, guys. That was great. I think we can get into some Q&A. So go ahead and pop any questions you have in the Q&A box at the bottom of your Zoom window, and we will try to answer as many as we can in the next, let's see, 15 minutes or so. All right, so the first question we have is for Apoorva. Have you tested the ability to identify items to the level of detail in the California SB 54 covered material categories list? So, can this be used in EPR audits?
That's a super question. That's something that we've been actively working on with PROs that are sort of creating these lists and are in the process of sort of finalizing them. There are several states now that have different material lists. So there's step one is sort of to harmonize that list into one, and then step two is to match it into the categories that we currently have. And then, step three is to build out the data set to be able to identify the objects that are not in our list but exist in one of these states' EPR covered material lists. So it's an ongoing process. Our goal is to have this be ready as these EPR programs roll out. Initially, the idea would be to monitor these in labs and facilities that the PROs will operate, do sort of sampling of material, but ultimately to be able to do live audit of materials in the facilities themselves, which is where I think the biggest value is for AI systems. Yeah, so we're actively working on that. If this is an area that you're interested in, we're happy to sort of jump on a call with you to see what your needs are and figure out if there's a way we can work together.
Awesome, thanks. So for the next question, I'm going to direct it over to Katie. This question says, curious about 95% accuracy. Does that mean when the AI identifies an object, it is correct 95% of the time, or can it identify 95% of objects? What percent of objects that pass the sensor does it fail to identify?
Great. Thanks, McKenna. Yeah, so the first part of that is right. Of any objects that pass under our camera, we're identifying, and of all of those, 95% are identified correctly. So I believe we're at around 60 unique sorts of material classes or packaging types that we categorize those materials into. And across those, we're 95% accurate.
Sweet. The next question is material characterization based on count or weight or volume. And how does a system convert an incidence of an object into weight or volume? And how accurate is that conversion? I think Apoorva can answer that one.
That's another really good question. A lot of MRFs operate based on mass and not based on counts. So there needs to be a way to translate, what we're measuring in terms of counts into weight, right? And there's sort of simple ways to do that, and there are more complex ways to do that. So we have been refining this over time, and for different object categories, we apply different methodologies. So for simple things like aluminum cans, of a certain size, the weights are very consistent. So you can just kind of simply do a conversion. But for more complex objects, let's say like an HDPE container, there are different types of HD containers, and they're, depending on what you're measuring, it might be of a different weight. So you can kind of do a regression type of an analysis, kind of sampling different containers, putting them into categories and coming up with weights in them. And then there are really hard objects to weight, right? Like there are things like paper and cardboard that, either, you can't see the depth, how big it, how how many stacks of paper, how many sheets of paper there are. So, from the top, when you look at it, it kind of looks like a sheet of paper. It might be a book, and the weight of a sheet of paper and a book is very different. So those are extremely hard to characterize. So I would say it depends on the accuracy depends on the material classes. For sort of standard classes, easy to convert classes. They're well over 95% in terms of how well we can convert to weight. In terms of sort of containers, we're getting close to 90% in terms of being able to convert to weight. In terms of paper or cardboard, things like that, we're still work in progress. And what we typically do when weight is important is we do a calibration exercise and when we first initially install these systems to kind of understand the variability of what you're seeing in your lines and come up with a methodology that's most appropriate. So again, if this is an area of interest and you want to figure out weights more accurately, we're happy to work with you on that as well.
Perfect. Thank you. So the next question is, how can EverSlabs help with yield improvement or recovery for, and I could be butchering this word, polyolefins recycling facility, since the objects turn into shards after shredding? And I'll pass this one to Katie.
Thanks, McKenna. And you nailed the pronunciation there.
Awesome.
Yeah, it's a little bit of a different application. So in those plastic recycling plants, our visions would be used to monitor your in-feed. So the point of your process before that shredding happens, right? Because in order for our models to accurately identify what the material is, it needs to have certain features, distinguishable features about the object for us to properly identify it. So we would be put towards the in-feed of your process to sort of measure the incoming purity of the material before it goes into that shredding and cleaning process. And then that data ideally would be used to help you adjust your sorting downstream or adjust your processes downstream, whether you need to slow down some conveyors to perform a little more QC if there are a lot of contaminants, or redirect materials so that it doesn't end up in a batch and reduce the yields on that.
Cool. So we have another question for you, Katie. Would you need multiple cameras for a wider belt?
Yeah, depends on the size. So, if it's maybe over a 4-foot wide conveyor belt, we may need 2 physical cameras just to make sure that we're seeing all parts of the belt and not missing any areas of it. But all that data would still funnel into, the same data set. So it's not like you're looking at multiple dashboards for the fact that there's 2 cameras on one line. It's still considered what we would call one vision system. So it's giving you that one full data set.
Sweet. Next up, what are the limitations of the portable mount system in terms of burden of depth, volume, and belt speed? Have Apurva take that one. I think you're on mute.
Excuse me. Yeah. So one of the pictures that Katie showed was of a portable vision system. It was the compact vision system. We use that in a couple of different ways. We use that as to sort of a means of a quick data collection on a line, just to give us an idea of what to expect. That's one way we use it. Another way to use it would be to use it in tight spaces where there isn't enough room for a complete vision system. The limitations, so a vision system typically goes with a compute panel. Like I mentioned, we're running these models in your facility at the edge. There's a computer somewhere that puts data. Now, setting up that computer requires some time. It requires network connections. And oftentimes, that can delay a project. So if we want to do quick vision data collection, the portable vision system just records data within itself. And after a day or a week or a month or whatever time frame we decide is appropriate, we come back, we take take that unit back, and we can download the data and run the models and to get sort of the analysis on that line, right? So that's the most ideal use case for the portable vision system. The limitations really are you don't get live data. You're basically relying on someone coming and taking that data and then processing it after the fact. If you wanted live data, we can install cellular modems to kind of get that data through a cellular connection. But those are limited sometimes in terms of how much data you can process just because of the cost. So sometimes, if you wanted more real-time data, you can get it within periods of time. So those are some of the limitations that you're working with on the portable vision system.
Great, thank you. Bringing it back over to Katie, the question is, does your company or another vendor provide the robots that pick out the materials?
Yeah, great question. So this webinar focused on AI and the use of our camera and our models to provide that data and insights in a MRF. But we do have an entire robotic solution as well, which is paired with these cameras, right? So all of the objects that the camera is seeing and all of the decisions on what a material is, if it should be in that stream or on that conveyor, can be then used to instruct a robot a few feet past the camera on the same line to either on a QC line, pick contamination out of a stream, or to do positive sorting as well. So on a last chance or residue line, it can recover recyclable objects like UVC, PET, anything that your entire system may have missed. It can pull that out of the stream and avoid you sending that to a landfill. So we definitely have that piece. And it wasn't something we focused on today, but would love to, connect with that person who asked that question directly if they want to learn more.
Yeah, and we also have a bunch of other webinars we've done on our YouTube, and some of those have focused more on our robots. So if you guys want to go check that out, we have quite a few webinars you can look at. So the next question for Apoorva, how many vision systems do you need for a mass balance view of your facility?
I'm muted again. Another good question. So it really depends on what out, sort of the precision of the information you're looking for. Typically a mass balance, you need to look at, where things are coming in and where things are leaving, right? So the source and the destination. So, at a minimum, you need about 3 locations that you're sampling data off. So somewhere where materials are coming in to your processing, your sorting equipment, one in sort of the QC or the baling stage of that commodity that you're looking for. And then the third is on the residue or the last chance line. So with that, you can get a decent idea of a particular commodity flow, one single commodity. Now, that commodity may be missorted and ending up in other, material streams, other QC areas, other balers. So if you want a more accurate assessment of those materials, then you want to put vision systems in those QC or baling location as well. So, kind of a minimum would be 3, probably a typical would be about 6 locations that you're sampling to get a decent idea of how your commodities are flowing around in your facility.
Awesome. I think that's it for our Q&A. If there are any questions we didn't end up answering, we will reach out directly to you over email. And if anyone has any additional questions that pop up, after this, or maybe you didn't put them in the Q&A, feel free to reach out to Katie or Apoorva. Their emails are up on the screen right now. Or I'll be sending out a recording of this webinar next week over email, and you can go ahead and respond to that email if you have any questions that pop up. So thank you guys all for joining, and keep an eye out for any webinars we have in the future. Have a good rest of your week. Thank you.